This question is given in gate 96, the first one, and then gate 2014. They are saying that we have a table, relation table, which means this one, which is having a, b, c, d, e, f, all these attributes. And now they are saying if these functional dependencies hold on the database, then what might be the key? They are asking about the key. So what is a key? Key is anything using which I'll just see this. Key is anything using which you should be able to determine all the other attributes uniquely, isn't it? Which means if you take the key, whatever you think is the key, and if you apply closure properties, which means you take the closure of the key attributes, then whatever attributes you get, they all should be covered, right? So what all should be covered of the table, right? Now the table is containing a, b, c, d, e, f, and now they are saying that these are the functional dependencies and the options are given. And one easy way to answer this question is you take each option and you find out the closure that solves it. Find closure of cd plus, ec plus, ae plus and ac plus, right? Then you are going to get some answer, right? And if only one of them is going to give you all the attributes, that is going to be the key. That is one way to answer it. But then maybe let's see how this really works, how to find out the candidate keys, how does it really work, the concept of it. See, now I don't know what is the candidate key. Let us say there are some one attribute or a collection of attributes which are going to be the candidate key, right? And now if I take the closure of this, I am supposed to get all the attributes on the in the table. What are the attributes I am supposed to get? I am supposed to get a, b, c, d, e, f. These are all the attributes I am supposed to get, right? Now my question is this: where do you really get these attributes from? So one thing is, whatever of the attributes that are present in the here left side, we are going to get all the attributes here, isn't it? Which means if I start out with, let us say, ab plus, then I'll definitely get ab here. So whatever are present here, I'll get them here. That is one thing. And the remaining attributes I get from the right hand side of the FDs, which means remaining attributes all should come from the right hand side of all the FDs. There is no other way I can get them, right? Are you following it? So now I don't know what to put here. Fine, leave it. Which means I don't know what comes from left side of this equation to the right side. I don't know that. Fine. But then somehow I should get whatever are present on the right hand side of the attribute of these FTs into this. I hope you are following. Which means, see, simple. Only way we can get all the attributes in the closure set is whatever is present in the left hand side of what this key. So if you expect AB to be the key, you are going to get AB, and all the other elements should come from the right side of the FDs. That is how the entire concept is defined, isn't it? Therefore, what are all the attributes that I could get from the right side? I could get F, right? And I could get A. See, why am I doing this? It all makes sense at the end. Just watch it, okay? I'll get A and I'll get D, isn't it? And I'll get B, right? Fine. Now you could have some attributes here in such a way that you can derive all these attributes. So what are the attributes that are derivable? A, B, D, F. So somehow you can get these attributes from the functional dependencies from the right hand side. But then there is no way you could ever get D, C and E from that functional dependencies. No other attribute is going to determine C and D, right? So only way if you could get C and D is from the left side itself, only from here, right? So if you want to cover all the attributes, you should definitely have C and D here. Without C and D here, you could never cover C and D. Are you following this? I'm just going in a procedure right now. Therefore, the starting step is your key, whatever is the key, should definitely contain C and D. Why? Whatever is the key, it should definitely get C and D. The reason is there is no other way you will get C and D covered unless you include them as a part of the key. Got it? So the starting step is maybe whatever is the key, you should contain C and D. Now I'll test whether just C and D are sufficient. See, minimum you need C and D. I want to test if C and D are sufficient that I could get everything there, right? So one thing is for sure, surely every key, either it is a candidate key or a super key, whatever key it is, they should definitely contain C and E for the table, otherwise they'll never be covered, right? So with this knowledge you can directly go and test the answers, isn't it? See this. Now this one doesn't contain E, so there is no way you can get E here. This one contains CE. It might be the case, it might be the answer, I'm not sure, it might be the answer, right? And this one doesn't contain C, therefore it is not. This one doesn't contain E, therefore it is not. So all these three are definitely not going to be the keys. So definitely this should be the answer. No, in order to answer this question I can mark it as answer, but then in general you should not say that it is key unless you find out the closure. Now I want to find out the closure of CE. Now what does CE contain? CE plus contain, one is you should add CE, and because of C, F gets added, right? And because of E, A gets added, and because of CE, D gets added, and because of A, B gets added, right? Therefore I covered all of them, right? So CE is going to be the candidate key for this table. And now one interesting question is, how many candidate keys will be there for this particular question? Is C the only answer, or are there even more? Okay, first of all, how many possible candidate keys will be there? I mean, how many subsets of these attributes are possible? 2 power 6 minus 1, which is nothing but 63. So 63 combinations are there. You might have to observe all of them, right? But we are not going to do that, don't worry. Okay, now out of these 63, I can classify them into two types, right? One is set of all subsets which contain CE, and set of all subsets which does not contain CE, right? So the set of all subsets of this which does not contain CE are definitely not in the race. They are out of the race, right? And what are remaining now? The set of all attributes which contain CE, right? Now even in the set of all attributes which contain C and E, they should be combinedly present, isn't it? So if they contain only C, right, only C or only E, which means right, and then contains both C and E, right? So this is not containing either C or E, this is containing C and E. Now if they don't contain C, or if they contain only C or only E, they are not possible, they are not capable to be eligible to be candidate key, right, or any key in that manner. Now if they contain both C and D, yes, they can be the keys, isn't it? Therefore out of all the keys which contain both C and D, C is the minimal key, therefore C is the candidate key. So if already C is the candidate key, whatever contain both of them are just going to be super key, right? Therefore out of all the candidate keys, only one key is possible, that is CE. Therefore we have only one candidate key, right? And what about the super key? Super keys are anything which contains CE as a subset. Now how many attribute combinations are possible which contain CE as a subset? You remove CE, then how many are remaining? 1, 2, 3, 4, right? Therefore 2 power 4, which means 16 super keys are possible which contain CE in them, and only one candidate key is possible. Got it? And that key is that candidate key is CE itself. See, I don't know if you are understanding this or not. In simple words, definitely any key, either it is a candidate key or super key, if it has to cover all the attributes, it should definitely contain CE, because CE is not covered by any one of them, isn't it? Therefore CE should be present in the key, right? In case if CE is present in the key, and if CE is going to be a candidate key, then it will be the unique minimal, which means every other key is supposed to contain CE, and now CE turned out to be the minimal key, right? Therefore what can we say? CE is the candidate key, and everything else which contains CE is going to be the super key. Got it? So we got only one candidate key and 2 power 4 super keys. I think you understood this. Why 2 power 4? Because if I remove C and E, right, then how many elements are there? 4 elements are there. Then every super key can contain any combination of these 4. And how many such combinations can I get? 2 power 4, 16. Therefore 16 super keys and one candidate key is possible for this question, and it varies from question to question. Okay, fine.